Hi, this is Dr. Chen, and for this particular video, we're going to talk about estimation methods, as well as introducing the unconditional means model, which is the first type of multi-level model that you would want to fit prior to adding additional level 1 and or level 2 types of predictors. Similar to previous videos that I've made so far, I just want to let you know where my sources are coming from. For this PowerPoint presentation, a lot of it is adapted from Singer and Willett's 2003 textbook and webpage over here, so feel free to check that out. And in regards to the R syntax, for this particular tutorial, as well as actually a couple of other future tutorials from chapter 4. We're gonna use some of the syntax written here by Clayford. And this is the website for which I was able to get this syntax from. And so feel free to check that out too. It seems like a really good resource. And the reason why I went with this person's syntax is because the function that we're using would actually enable us to get estimates that are more similar to the estimates that are printed here in the textbook, as opposed to the syntax and the functions that are used by the UCLA Consulting webpage. Those numbers tend to differ a little bit, partly because I think they're using a different type of estimation method for the particular replication. So speaking of estimation methods, I want to quickly talk about the common estimation methods here. Broadly speaking, they tend to be divided into maximum likelihood and generalized least squares, and we get different derivations out of it. So let's talk about generalized least squares first. Similar to ordinary least squares, GLS is looking for parameter estimates that is going to minimize the sum of squared residuals. Different from OLS, GLS is not going to require your residuals to be independent and homoscedastic. GLS actually allows the residuals to be autocorrelated and heteroscedastic, as in, similar to the residuals that we have in the composite multi-level model for change. So very briefly, the way in which generalized least squares works in terms of its estimation methods, first of all, it's going to try to fit the composite model, the composite multi-level model, by regressing the outcome based on predictors using ordinary least squares first, actually. And then based on those estimates, it's going to estimate the error covariance matrix using the residuals from the OLS fitted models. And then it's going to refit the composite model again using GLS, treating the initially estimated error covariance matrix as though it was the true error covariance matrix. So in other words, there are two stages to the way in which GLS is attempting to find the best parameter estimates here. The first stage is to use basically ordinary least squares to provide the starting values or the initial estimates of the fixed effects. And then the starting values will then yield the predicted outcome values that allows the computation of the residuals for each person for every occasion. And so the population error covariance matrix is then estimated using these residuals. So that's the first stage. In the second stage, is going to go ahead and compute the revised GLS estimates of the fixed effects and the associated standard errors under the assumption that the initially estimated error covariance matrix from the first step is the correct representation of the population error covariance matrix of the composite model. So basically 2 steps. That's the way in which GLS is seeking those parameter estimates that minimizes the sum of squared residuals. There's a derivation of GLS, which is iterative GLS. And so iterative GLS is basically, instead of just stopping after one round of estimation and refitting in that two-step approach, you're basically going to ask the computer to implement the approach repeatedly, each time using the previous set of estimated fixed effects to re-estimate the error covariance matrix. And then it'll keep doing that to the point whereby there is not much more not that much more precision that is added to your parameter estimates. So it's basically repeating that process multiple times for iterative GLS. So that's GLS in a nutshell in regards to how it's seeking to estimate those parameter estimates. Maximum likelihood, on the other hand, is going to seek those parameter estimates that maximize the likelihood function, which assesses the joint probability of simultaneously observing all the sample data that is actually obtained. Now, there are actually two types of maximum likelihood estimates. There's the full, and then there's the restricted maximum likelihood. So either FML or RML. The difference between full and restricted is that the restricted maximum likelihood is actually being a little bit more precise by accounting for the uncertainty associated with estimating the regression parameters, so the fixed effects, before estimating the residual variance. And so in other words, with full maximum likelihood, it is simultaneously estimating the fixed effects and the variance components, whereas with restricted maximum likelihood, we are actually sequentially estimating the fixed effects and then the variance components, because it recognizes that the fixed effects have some amount of uncertainty with the estimation, with its estimation. GLS also has a restricted version of GLS. So that's basically the GLS equivalent of restricted maximum likelihood, basically recognizing the fact that the fixed effects have some amount of uncertainty to them. And so it incorporates that into its algorithm. So between, and this is an important distinction here between like full versus restricted, regardless of whether if it's maximum likelihood or GLS. What's the main difference here? So some researchers say that the restricted methods is actually more intuitively correct because we're being a little bit more honest with the uncertainty that goes into the estimation of fixed effects here. But there really so far hasn't been any like solid proof that the estimates coming from the restricted approach is more precise compared to compared to the full approaches in practice. In fact, if the usual normal distribution assumptions required for the maximum likelihood estimation holds, GLS estimates are actually maximum likelihood estimates. The take-home point over here is different software programs, depending on whether you're using Melvin or HLM, or if you're using SAS or Stata. We're actually going to be using R for our demonstration here. You probably want to know what is the default estimation method that's been used for your software. So this is one of the reasons why I'm going with the syntax that was created by Clayford, as opposed to the syntax that is suggested by the UCLA Computing Consulting Group. It's because with the syntax that's provided by the UCLA Consulting Group, I believe they're actually, the particular functions that is used to estimate the parameter estimates is restricted maximum likelihood, I believe. And so because of that, the parameter estimates are a little bit different compared to what is reported in chapter 4. Whereas the function, the LMER function, which is what we're going to use for our demonstration here, we can turn off the restricted maximum likelihood as the default. And so we're going to be using full maximum likelihood for our parameter estimates. And the reason why I prefer personally the full approaches is because then when you look at goodness of fit statistics later on, so goodness of fit statistics are basically global indices that give you a global sense of how well your data is being able to account for the variation in your data set. So if you're using the full approaches to estimation methods for the maximum likelihood or GLS. The goodness of fit statistics actually applies to the entire model, both the fixed and random effects. And so that's the reason why I like to use this. Whereas if we were to go with the restricted approach, yes, I mean, technically, they're a little bit more precise in terms of the estimation approach there, but the goodness of fit statistics apply only to the random effects. And so we can only test hypotheses about the variance components as opposed to the fixed effects components. So a little bit less flexibility here in terms of being able to how we should interpret the goodness of fit statistics. We'll talk more about goodness of fit statistics in another video after we go through a couple of different models of multi-level modeling. So speaking of different models of multi-level modeling, let's talk about the first model that you should always fit, regardless of what your actual model is. The first model that you should always fit is the unconditional means model, which is shown right here by the level 1 model parameters and the level 2 submodel parameters. With the unconditional means model, we're stipulating that at level 1, right here, the true individual change trajectory for person I is actually completely flat, and it is sitting at an elevation of pi subscript 0 I. And that means to say that the trajectory has no slope. And so there's no slope parameter associated with any type of temporal predictor, so it can't really tilt. So it's basically a flat line. The single part of the level 2 submodel right here stipulates that while the estimated true change directory, let me have another go at this. The level 2 submodel stipulates that the estimated true change directories may differ in their elevation compared to the average elevation across the population. So the average elevation across the population is actually represented by gamma subscript 0, 0. And then zeta 0I represents the deviations of each person in terms of their change trajectory from this population average trajectory. So again, technically, you would hope that this is not the model that is giving rise to your sample data, because you're basically saying that the best way to account for the variation in data is to say that there's that every person has an estimated true mean, which you are allowing, because of this epsilon ij over here, you are allowing each person to have some variation there, but you're not allowing any type of slope in there that goes together with time. So this is not really a model that is representing any type of relationship between time and your outcome of interest here. The reason why we fit this unconditional means model is to really have a better understanding of how the variance partition operates. And so let's see if we can kind of have another go at this again. The true mean of y for individual I is pi subscript 0 and I, right? So that's the estimated true mean of y for every individual. It is pi subscript 0 and I, and then you have the epsilon ij in order to allow each person to have their individual variation. And we also assume that epsilon ij is distributed normally with a mean of 0 with a specific type of variance associated with it. Whereas the true mean of y across everyone in the population is represented by gamma 0, 0. So these two things are the same over here. So gamma subscript 0, 0 is representing the estimated true mean of y across everyone. So borrowing some terminology from analysis of variance, pi subscript 0i is the person-specific mean, whereas for gamma subscript 0, 0, this represents the grand mean across individuals and occasions. So the unconditional means model basically says that the observed value of y for individual I on occasion J is composed of deviations from these means. On occasion J, on any particular occasion, the estimated alcohol use deviates from the individual's estimated true mean by epsilon ij. This level 1 residual over here is also called the within person deviation, because this captures the distance between yij and epsilon subscript 0I. And then for person I, their estimated true mean is going to deviate from the population average, and that's captured by zeta subscript 0I. This level 2 residual is also known as the between person deviation that assesses the distance between the pi 0I and gamma 0. So if you were to basically combine the level 1 submodel and the level 2 submodel, so substitute these parameter estimates into here, what you get is basically yij, which is the estimated alcohol use for every person at a particular occasion. It's going to be a function of the grand mean across individuals and occasion that's coming from here, plus zeta 0I. So this represents between person deviations, and then epsilon ij, this represents the within person deviations from the level 1 submodel. And this is actually the results of fitting this unconditional means model to the data. We can see over here that gamma 0, this represents the intercept. So the intercept, again, this is the grand mean across individuals and occasions. So it is basically the average of alcohol use across individuals, across occasions, and it is statistically significantly different from 0, suggesting that this is more than 0. And then we have the within person variance components, and then we've got the between person variance components over here. So sigma with subscript E over here, this represents the within person variance, so that's coming from the level 1 submodel. And then sigma with subscript 0, this represents the between person variance. Now remember, with the level 1 variance component, this represents the difference between the estimated true mean of alcohol use for a person and their actual score. And so that's epsilon ij, because epsilon ij is assumed to be distributed normally with a mean of 0 with a particular variance. This is the variance estimate over here. And then this is the variance estimate for the level 2 submodel, which is the scatter of each person's estimated true mean from the population's average true mean. So we got the within person variance and we got the between person variance. Let's take a closer look at these two variances here, keeping in mind that epsilon subscript E, sigma subscript E represents the variation that is unexplained by your level 1 submodel, and sigma subscript 0 represents the variation in your level 2 submodel that is not accounted for. So the reason why we fit the unconditional submodel is explained by this slide over here. We are actually really interested at the between person variance and the within person variance, because the between person variance is going to let us know if there is sufficient amount of variation between individuals regardless of time that is worth explaining. Because if this estimate over here, if the estimated between person variance is statistically significant, that means that there's still quite a bit of variability that is unaccounted for by our level 2 submodel. That means that we should, the next step is to enter some level 2, is to enter some between group predictors to be able to do a better job and being able to account for the between person variance in the level 2 submodel. Similarly over here, this tells us if there is a significant amount of variation within individuals over time that is still unaccounted for. Because if this is statistically significantly different from zero, that tells us that, hey, maybe we should check out some, time varying predictors that we should enter into the level 1 submodel in order for us to account for this statistically significant estimate of the variance that is still unaccounted for. What we can also do is that we can sort of estimate the proportion of the total variation in your outcome that lies between people and within people. So in this particular example, the formula is really simple. We're just taking the estimated variance of in Y that lies between people, which in this case is 0.564, divided by the estimated between person variance and the estimated within person variance. So this two in total is supposed to give you the total amount of variation. And we just basically want to know what amount of this total amount of variation is actually attributable to between group differences. And so if you take this, we actually get 0.5, which suggests that 50% of the total variation in alcohol is attributable to between group differences between the adolescents. And so that gives us, again, it sort of gives us like an effect size of how much importance should we put on trying to enter in between group predictors and within group predictors. The interclass correlation over here will help us kind of answer that. So in another video, we will actually add in another parameter, and it actually a few parameters, including the stochastic components, to figure out what does time, how does time play a role in all of this? Because so far in the unconditional means model, we have no slope. And so we're kind of making the assumption that that the best way to capture the individual's true estimated alcohol use is to just look at the grand mean, which obviously is not the most precise way to look at things. So more about fitting the next model in another video. But right now, I just want to very quickly demonstrate how to recreate the table right here that we just saw. So remember, we have gamma 0, which represents the grand mean of alcohol use across individuals and across people. That's the fixed effect. And if you look at the stochastic components, we've got within person variation, and we've got the between person variation. And you want to know if these two outcomes are statistically significant. So we know the results over here. I'm just going to try to recreate this in RStudio and kind of show you like how they correspond to each other, so that when you try to fit your own unconditional growth model on your particular data set, you sort of know what are the steps to do this in RStudio. So let's get out of PowerPoint. Let's go to RStudio. And the first thing that you want to do is you want to install the package LME4, and then you want to load it into your library, because we're going to be using the LMER function in order for us to fit the unconditional growth model here. So the unconditional growth, the LMER function, what it basically is that it's a function that is a linear mixed effects type of function, where it's going to allow the within group residuals to be correlated and or to have unequal variances. And so that's going to be very similar to the nature of the residuals that we would assume to exist within the context of a multi-level model. And I just have a note over here that this function that we're using, the LMER, is different from the one recommended by the UCLA Statistical Consulting Group's website, because this function actually allows us to use maximum likelihood or full maximum likelihood as the estimator, instead of having to rely on restricted maximum likelihood. And this allows us to get numbers that are going to be closer to book, and also goodness of fit statistics that applies to the fixed effects as well as to the stochastic effects. So let's call this model.a1. The function is LMER. We're gonna regress alcohol use actually on a constant, because we expect alcohol use to not be influenced by any type of predictor. We're just kind of looking at the grand mean over here. So alcohol use regression 1 as a constant, and we're going to specify what the stochastic components are. In this case, we just enter in our constant again, followed by a vertical bar, NID. What this tells the computer is that we're setting the residuals at the level 1 and level 2 submodels to come from a mean of 0 and to be univariate normal, which is sort of what we just talked about just now. Data set is alcohol 1, and we're going to turn off the restricted maximum likelihood as the estimator. So say false, and then it's gonna fall back on full maximum likelihood as the estimator itself. And to get the results, just use a summary function. And so here we go. So you've actually got a few goodness of fit statistics. We'll talk more about AIC, BIC, and the deviance statistics in another video. But for right now, let's just focus on the fixed effects and the random effects. So the fixed effects is 0.92195. It gives you a t-value together with that as well, which if you were to compare that with a t-table, it'll let you know that it is statistically significant. And then for the random effects, so we've got the level 1 residual. So that's referring to this right here, sorry, that's referring to sigma subscript E, I believe. Yeah, subscript E. And then we've got the between person variance that is unexplained for. Now, let me go back here again. So I've actually copied and pasted a screenshot of that into here just to show you again the correspondence. So this represents the fixed effects over here, gives you a t-value, which if you look at a t-table, you can figure out if that is p less than 0.05. And in this, if you look at the t-table, this represents the within the word residual. It almost always represents the residual at the level 1 submodel. So that's the within person leftover variance that is unaccounted for by our level 1 by your multi-level model. And then this variance over here, this represents the between individuals type of variability that is left over, that is unaccounted for by your multi-level model. And as you can see, the parameter estimates are fairly close over here. Now, you may also notice that if you were to use this particular function that we're talking about, it doesn't actually give you directly what the statistical significance values are, but it does give you the standard deviation. And so it's not that hard at all for you to figure out what the statistical significance is, as long as you know the standard deviation and the sample size. So you could make something like this, and I'll post this into a step so you can have this as well. Just gonna plug in the variance and the standard deviation. It's shown over here. So the within person variance is, come back here. Within person variance is 0.5617. And the between group variance is 0.5639. And standard deviation is 0.7495. And standard deviation for the between group variance is 0.7509. Okay, so we got n, so we got 82 people. We just take the square root of n, which is basically the square root of the respective cell. And to get the standard error, we just take the standard deviation divided by the square root of n. So that's what we've done over here. This standard deviation divided by the square root of n. And the t-value is basically the variance estimate divided by the standard error. So it is the variance estimate divided by the standard error, which gives you the t-value. And so each of these tests over here is going to constitute a one sample t-test with n-1 degrees of freedom. So if you have your own t-table, you can look at that. If not, this is a website called t-table that will actually help you figure that out. So I put over here, 81 is a degrees of freedom. Significance level is 0.05, and it'll actually give me what the t-value is for it to be statistically significant. Or you can also look at this particular table here and have some estimate based on the degrees of freedom and whether it's a two-tailed test or one-tailed test. So is this the critical value is, I might have messed it up. So 1.9897. For this one. So our value is definitely larger than 1.9817. So yes, it is statistically significant for both of them, meaning to say that the leftover variance within the person is still quite a bit, and the leftover variance for between groups is actually still quite a bit as well. And if you were to actually look at the intra-class correlation right here, because the intra-class correlation is 50%, so you would probably benefit from fitting a between group type of predictor, as well as within person type of predictor as well. So in other videos, especially for chapter 4, we're not gonna play too much with adding time varying predictors into the level 1 submodel to capture more of the within person variance. We're actually gonna play around more with the between person variance, and we're gonna add in some predictors and some interaction terms for us to do a better job of being able to capture the leftover between person variance that is still unaccounted for, at least based on our unconditional means model. So after this is going to be about how can we build an unconditional growth model, and then we're going to start adding other predictors in there. So it is an iterative process. Like I said before, regardless of what your actual model for change is, the first thing that you want to do is to be able to fit this unconditional means model, because it'll help you figure out how much of the variation is coming between people and how much of the variation is coming within people, and that can help you figure out what types of predictors you would want to enter into a model. So it's like you kind of are at a fork of a road, and you're trying to figure out which is more important here, between person variability or within person variability, and this will help you point you in that direction. So that's all for this video. I hope that was helpful. Let me know if you have questions.